Hi, everyone. Welcome and thank you for joining us for AstroTours. My name is Simran Raval. I'm a PhD student at the University of Toronto, and I'll be your host for tonight. I would like to begin today's event with a land acknowledgement. So I am tuning in from Toronto, which is situated on the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. The territory was subject to the Dish with One Spoon, One Plum Belt Covenant, an agreement between the Iroquois Confederacy and the Confederacy of the Ojibwe and Allied Nations to peacefully share and care for the resources around the Great Lakes. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and I'm grateful to have the opportunity to work on this land. Acknowledging the traditional territory on which we live and work is a small but important step that reminds us to learn more about the Indigenous peoples in these regions, to consider the history and ongoing colonialism on this land, and to reflect on how each of us can contribute to reconciliation. We're lucky enough today to have people tuning in from across the country. You can land and who's got land to learn more about the land that you're on and who it belongs to. So if this is your first time attending AstroTours, we generally run our tours on the first Thursdays of most months. Today, we'll be having our talk by Taylor Kutra. After the talk, we'll be heading over to a Zoom room for a variety of activities and demonstrations, ranging from virtual telescope tours to showing you how you can use Zooniverse to participate in real science. AstroTours is organized and run by graduate students in the Department of Astronomy and Astrophysics at the University of Toronto, and supported by volunteers who are undergraduate and graduate students in astronomy and physics. We run AstroTours to share our passion, so we really value feedback from our attendees. After the event, please go to bit.ly/AstroTours to give us your feedback. And throughout the talk, please put your questions for Taylor in the YouTube chat. So before we get into tonight's event, I'll first let you know about some upcoming events. So next month in March, we have a very special AstroTours for Earth Hour. We'll be announcing our speakers leading up to the event on social media, so make sure to check for those posts. You can learn more about Earth Hour at earthhour.org. The event will be online, and it will be on Saturday, March 26th at 8:30 p.m. EST. Some other events that are upcoming would be from the Dunlap Institute. They're having a virtual Astro Trivia night on Tuesday, February 8th at 7 p.m. EST. They also have a Cosmo for Your Couch video series coming out. And our speaker tonight, Taylor, she has a video for Cosmos from the Couch on protoplanetary disks that's also coming out next week. So make sure to check out the Dunlap Institute Facebook page for more information. There's also a variety of online events being held by the Royal Astronomical Society of Canada, and you can visit their website for more information. So now on to tonight's event. Our speaker is Taylor Kutra. She is a PhD candidate in the Department of Astronomy and Astrophysics at the University of Toronto. She did her undergraduate degree at Quest University, Canada in British Columbia, where she studied physics and astronomy. When she isn't doing astronomy, she spends her time backpacking, paddling, climbing, and taking care of her rescue dog, Shanty. I'll now pass it off to Taylor to tell us about women and gender minorities in astronomy.
Hi, thanks for that, Simran. Let me go back. Here we go. Great to be here. It's so nice that AstroTours is up and running again, and I'm really excited to be here tonight. I hope everything is looking good. I believe so. Okay. So yeah, as Simran said, I study protoplanetary disks. They're this disk of debris that surrounds a star after it forms. And what you're seeing here are actually along the side some pictures of them that we've taken with the Atacama Large Millimeter Array, which is this giant telescope in the desert in Chile. And as you can see, they have all of these wild features like arcs and rings and gaps. And what I do is I try and make these features using simulation. That's what's in the center here is a simulation I've run. And so, you know, I was planning on giving a talk about this stuff. But then I got a message from Simran and Isha, the coordinators, the directors of AstroTours, and they asked me, so they said, hey, Taylor, since it's the International Day for Women and Girls in Science coming up on February 11th, would you mind featuring some women in astronomy that have contributed to your field? And I said, that's a great idea. I would love to do that. And then I was thinking about it a bit, and I was like, well, I could probably count the number of women that I know in astronomy who have made these like field-changing contributions on two hands, the kinds of women whose names were in my textbooks. And I saw that as a bit of a problem. So I asked them if I could instead save the talk about this for another time and do that instead. So, that's how we got to here. Sorry, there we go, here. So instead today, we're going to be talking about women and gender minorities that have made big contributions to astronomy. We're going to be talking about the people, and we're also going to be sort of like linking them together through their science. And we're going to be doing it by starting out sort of on a large scale. We'll look at galaxies, and then we'll go smaller and smaller and talk about stars. And then finally, we'll talk about planets. Great. So starting off, we're going to talk about first, probably the most well-known of the women astronomers today, and that's Vera Rubin. She's really well known for this observation she made that basically confirmed the effects of dark matter in galaxies, and we'll dive right into that. But if you're looking at this photo right now and you're thinking, wow, that's a cool telescope, I would love a tour of that. You can join the Zoom rooms because they're actually going to take you to this exact telescope at Kit Peak, and they'll show you around on a virtual tour. So that's pretty fun. But so of course, before we really get into what Vera Rubin was able to do and the measurements that she made with this telescope, we have to take a step back and learn a bit about spectrum. And so when you look at a star, stars basically produce light at all wavelengths, which we just see as like a bright, semi-colored object. But if you were able to take that light that you see from a star and you were to split it into its components, say by putting a prism in the middle of it, you would end up with something that looks like this, a rainbow. That's actually just a spectrum. You take the light from the star and you split it up into all of its different wavelengths, and you can look at them individually. Now, if you had a different sort of situation where you weren't looking directly at a star, but maybe instead you were looking at a cloud that was kind of right near a star, what's actually going to happen here is that the photons from the star are going to penetrate into the cloud, and those photons are going to collide with electrons that are in atoms in the gas. And when these photons collide with these electrons, they can actually, the electron, if the photon has the very exact right amount of energy, the electron can absorb the photon and move into what's called an excited state. So it stays there and it's excited for a little while. And then after a certain amount of time, it decays back into its ground state where it's happy. And when it decays again, it emits a photon. So if instead you were able to look, if you looked at a cloud where you knew this process was going on, which is basically most clouds that are being illuminated by stars, and you took a spectrum, you would have something that looks like this. There we go. You would only see light at these very specific colors, which corresponds to a wavelength, which corresponds to an energy. And that energy is the energy that the electron loses by jumping down, by becoming de-excited. And so, these lines, this light is actually being emitted by the gas. So we call them emission lines. And now, because this light, these emission lines, they're at these very specific wavelengths that correspond to these very specific transitions inside of an atom, we know that if they're not exactly where we know they should be, something's going on. So for example, if instead we saw the lines here, well, that's a shift to the blue side of the spectrum, which we call a blue shift. And it actually means that the cloud, the thing that's making the light, is moving towards us. Alternatively, if we were to see the lines on the other side, well, that is a shift to the red end of the spectrum. We call it a red shift, means that the cloud is moving away. So it's this basic thing that Vera did when she was looking at clouds in the Andromeda galaxy. And by the degree of this shift to the blue side or to the red side of the spectrum, you can actually measure how fast the cloud is moving towards and away from you. And then you can do things like what she did. So this is the big paper. What you're seeing on this plot here is rotational velocity along the y-axis. This just means how fast the stars are moving around the center of a galaxy. And then on the x-axis, this is the distance to the center. So what we're seeing here is how fast our star is moving as a function of how far away they are from the center. And this is what they saw. They looked at Andromeda Galaxy, which is the closest one to us. And they looked at these clouds and they made this plot. And if I had to summarize this paper in one sentence, it would be that the Andromeda Galaxy rotates weirdly. And you might be thinking to yourself, well, Taylor, the line looks pretty good. Like nothing about that is screaming weird to me. It's only when you get to know, when you understand what we knew at the time. What we knew at the time was all based off of the orbits of planets in the solar system. And we thought that stars and galaxies should just orbit like planets in the solar system. And that this, curve would look the same as if it was, just a big solar system. So we thought it would look like this red line. It's kind of just like a basic interpretation of what the speeds of planets would look like. And that's definitely not what it looks like. It's flat. And so to help you visualize how different this is a little bit more. So this is a little picture of how galaxies would rotate if they rotated like planets in the solar system. Planets in the solar system, the inner ones move fast, the outer ones move slow. Okay, but this is how they actually rotate. This is how Vera saw them. So the stars on the inner parts of the planet, or the inner parts of the galaxy, are moving just as fast as the stars in the outer part of the galaxy. So this is the difference between these two curves. And so Vera Rubin and her collaborator Kent Ford went on and they observed a bunch of other galaxies to see if, for some reason Andromeda was unique. And it turns out it's not. Most galaxies have these weird rotation curves that don't make sense if you think that galaxies should, orbit like planets do, or that stars in a galaxy should orbit like planets in the solar system do. Now, of course, the way we understand these curves today is this mysterious substance called dark matter. Dark matter fills up galaxies, but it doesn't interact with light. So we can see its effect gravitationally. In fact, this is the gravitational effect. But when we look at the galaxies, when we try to map out the matter that's in these galaxies, we don't see it. So yeah, and it turns out if you use the right model, the right distribution for dark matter in a galaxy, you can reproduce these curves pretty well. So we understand the effect of dark matter, but of course what we don't know is what it actually is. And one of the people who is working on figuring out what dark matter is this person, Chandra Prescott-Weinstein. She's a theoretical physicist at the University of New Hampshire who studies the early universe and, among other very cool things, wants to figure out what dark matter is. And so this is great. One of the facilities that's going to help people like Chanda figure out what dark matter is actually called the Vera Rubin telescope, or the Vera Rubin Observatory, sorry. And this is it. It's being built on a mountain in Chile, and it'll survey the entire night sky, and it'll find everything from like asteroids of interstellar origin to supernova and all these other magnificent things, which astronomers will then use to study things like dark matter, dark energy, the very early universe, everything. And it's one of the biggest telescopes, the biggest, new things that's coming to astronomy. So everyone's really excited about it. And it's great that Vera's name is on it. So next, we're moving on to stars, where we'll talk a bit about these two women, Cecile Pingapotion, I think I'm saying that right, and Margaret Burbridge. They helped us figure out what the sun, basically how the sun ticks, what it's made of, and how it makes the energy, why it's bright. And so again, one more plug. There's another woman who's typically talked about when we talk about, women in stellar astronomy, and that's Annie Jumpcannon. She did a lot of work classifying stars. So if you're interested in learning about that, there's going to be a demo about it tonight in the Zoom meeting afterwards. So to really understand what these two women did, we first, again, of course, have to take a step back to our crash course on spectra, because we have this scenario before we had the cloud off to the side. Of course, not all clouds are perfectly off to the side where we get these beautiful emission lines. Sometimes these clouds are in between us and the star. And so what you'll see when you look at a star is it's being filtered through the cloud. So we have the same story going on. We have photons from the star moving through the cloud. Some of those photons will collide with electrons, which will absorb those photons, and they'll move to their higher energy state, chill out, and then fall back down and emit a photon. But so when that electron absorbs a photon, of course, if we're along the line of sight, we're not going to see those photons. So instead of seeing this beautiful like rainbow spectrum, we actually end up seeing something that looks a little bit like this. These very specific wavelengths that mean the electron is jumping around in the atom are missing. And these create a feature that we call absorption lines. Now, sorry about that. It turns out that you don't need a cloud, separate from a star. It turns out the surface of a star is cool enough for some atoms to form instead of just being ions, where it's just like a nucleus hanging out. It can be a nucleus and electrons. If you look at any star, basically, you're going to see absorption lines because they can form on the surface of the star. But so back in the day, what people used to do is, if you see, you see a little bit of hydrogen in a star based off of these absorption lines, the different atoms have different fingerprints, they have different spectra. So you can kind of like put together a recipe book for what's inside the star, a little bit of this, a little bit of that. And people did that. And they said basically that the strength of those lines was proportional to the amount of that element in the star, the amount of that atom on the surface. And from that, they remarked that, oh, wow, the composition of the sun is a lot like the composition of the Earth's crust. And they're like, okay, interesting. If that's the case, then the sun probably has an iron core just like the Earth, which is, we obviously know that's not true these days. We know that what the sun is made of, it's hydrogen and helium, but someone had to figure that out. And the person that figured that out was Cecile Pingapotion. She was able to show that these very specific lines of hydrogen, these Balmer lines, they don't actually represent the amount of hydrogen in the star relative to like other atoms, because most of the hydrogen is ionized, which means that instead of, hydrogen being its atomic number 1, so it's a proton and electron when it's an atom, but when it's ionized, it's just a free-floating proton and a free-floating electron. And most of the hydrogen and helium in the sun is ionized. It's just free-floating nucleotoids hanging out. So what Cecilia did is she took this thing called the Saha ionization equation, which tells you basically in a gas at some temperature pressure, how much of a given element is in this like ionized form, where it's missing electrons or it has none at all, versus how much it's going to have its electrons. And so she did that, and she looked at the sun's absorption lines, and she was able to show that stars are mostly made of hydrogen and helium, which is such a basic, thing we take for granted these days. But I swear I had never heard of the person who did this before, prepping for this talk. And the last thing I just want to note is that this was her PhD thesis. Like, this is what she did at my stage in her career. And it just blows my mind that a PhD student was able to make a discovery that was like this fundamental. So of course, Cecilia went on to do great things. She became one of the first full professors who was a woman in the Faculty of Arts and Science at Harvard. And then she went on to be the first woman who was the chair of its astronomy department. So big things from her. And of course, we're talking about another woman. We're going to be talking about Margaret Burbridge and her co-authors. They basically took what Cecilia said about the sun being mostly made of hydrogen helium to write this paper, The Synthesis of Elements in Stars. And, to lots of people, doesn't look like much besides like a title, some impressive institutes, and then a couple of Shakespeare quotes, which like we don't usually do these days, but I feel like we're missing out on something. But basically what they did in this paper is they were able to go through the temperatures and pressures required to show that inside the sun, what's actually fueling it is fusion. It's hydrogen and helium, colliding with each other, colliding with other atoms or other like nuclei that are in the star to make different elements. So we'll back up a bit. The elements in the universe come from a variety of things. And this is how we understand them today, right? Some of them come from stars, some of them come from neutron stars, like other weird things that happen. But at Margaret Burbridge's time, this plot where, you can map out where everything comes from in the universe, it looked like this. They thought at this time that all of the elements that existed were there at the beginning of the universe. They didn't really have the same concept of a Big Bang, but they were like, okay, all of the elements that are here currently are the ones that have existed forever and will continue to exist forever. You don't make or destroy them. They're always just there. And now, of course, that's not true. And so what Margaret Burbridge and her collaborators were able to show is that you actually make these elements inside of stars. And it may not look like it, it doesn't cover the entire periodic table, but I will just point out that carbon, oxygen, nitrogen, sulfur, those are all of the elements that are like really fun. They make up our DNA. They're really important for biology. And they are all formed inside of stars, and then those stars explode, and then they enrich the surrounding environment. So Margaret was basically the one who figured out that we were star stuff, even though Carl Sagan gets credit for saying it, which he did, but she figured it out. Now, if you're wondering, Taylor, okay, how do we get from, this all the way back to this with all of these new things? And I will point out one thing, all of these squares that have a bit of orange on it, these merging neutron stars, this is a relatively recent discovery. And we know that because of this woman, this Maria Drought. She's actually a professor at the University of Toronto in my department. And when she was a postdoc, she and her collaborators got an observational counterpart for a neutron star merger. So neutron stars, these big, dense, wild objects in space. Two of them collided and exploded, or they merged. They didn't collide. They merged and they exploded, and they produced all of these elements that we weren't we kind of had an idea of where they came from. We thought this is how they were made, but this was the first observational confirmation of it. And so I, in preparing for this talk, I was like, okay, we'll get like a clip of the thing. And then I was scrolling through the paper and I noticed this is it. This is the merger. On August 2017, August 17th. It's bright. And then, 4 days later, it's dim. That's it. That was it. It was cool. I don't do observational astronomy clearly, but yeah, pretty neat. So now we're going to move on to women that study planets. We're also going to move a couple hundred years in the past to talk about Maria Kunitz. She was an accomplished German astronomer that wrote this book, the Urania Propitia. Now, there's this like really well-known story in astronomy from the 17th century about these two people, Tycho Brahe and Johannes Kepler. And this is this might be a little bit long-winded, but we'll get to Maria's things. The story goes like this. Tycho Brahe is like meticulous dude. He takes observations of stars and planets in the sky and he writes them down. He's really precise. He publishes these tables and says like, this is where this thing was, this is where this thing was, again and again and again and again and again, and world renowned for being precise. Then Johannes Kepler took these data points, and that was how he formulated his laws of planetary motion. He was able to figure out how the planets in the solar system orbit based off of Tycho's observations. And so if this sounds familiar, it's because that line that I drew on top of Vera's discovery earlier, that red line, that's Kepler. That's Kepler. So yeah, but what's left out of this story usually is that, Kepler figured out these laws of planetary motion and then published all of these tables saying, okay, this is where this thing is going to be in the future. Like, this is what my laws of planetary motion say. It's going to be here, it's going to be there, it's going to be there. But what was really well known at the time is that there were tons of errors in these tables, and that Kepler was obsessed with logarithms. I've never met a person who is obsessed with logarithms, but apparently they exist. So he had all these errors, and it was like really, really challenging to correct them because he used logarithms to make them. And so what Maria Kunitz did, she, saw Kepler's works, she saw his tables, and she saw the errors, and she was like, well, I'm just going to fix them. And so she fixed them. And in doing so, she also derived a simpler solution to figure out where the planets are going to be in the sky in the future. So that was great. And she also translated her book from German into Latin too, so that more people throughout Europe could, access the material and do stuff with it. She's been hailed as like one of the most like technical astronomers of the time. So it's really cool contribution. And now we'll move a couple hundred years into the future. And we'll talk about some women who worked at NASA. So beginning in like 1935, that's what my notes say, NASA, the precursor to NASA, started to hire women as computers. This was at a time, computers were not as ubiquitous as they are today, certainly, and, perform really rudimentary tasks. So when they wanted to do these like really complicated calculations for, various things, aerodynamics, flights, anything, they relied on people to do it. And so they started to recruit women. And so they performed these like really complex and tedious mathematical equations by hand. And they were known as the West Area computers. These three women are a part of that group. And they were an incredibly impressive bunch. So here we have, oh yes, they're also known as NASA's Hidden Figures. If this story sounds a little bit familiar, it's because there was a book and a movie about them a couple of years ago. So first we have Katherine Johnson. She was the first woman in the flight research division at NASA who received credit as an author of a research report. So before Katherine, all of the research reports that were produced at NASA were authored by men. And Katherine was the first woman to be the main author on it. Then we have Dorothy Vaughan. She was the supervisor of the West Area computers. And she was the first African-American woman to receive a promotion at NASA and to actually supervise a group of people. And then finally, we have Mary Jackson. She was the first African-American woman who was an engineer at NASA. Cool. But of course, this era was during the height of Jim Crow laws in the United States. And so these laws, they actually made it harder for NASA to hire Black women than white women. For example, if they wanted to hire a Black person, that person would have to take a chemistry course at a university before they could start. Whereas if the person that they wanted to hire was white, they wouldn't have to do that. And that's beyond, the regular segregation policies with regards to like facilities and access and all of these things. But, despite these and other adversaries, they did these calculations for various incredibly impressive feats at NASA, which includes putting the first American in space, which happened in 1961, where this person, Alan Shepard, went aboard the Freedom 7 flight. He went into space, but he didn't reach orbit. And then a couple of years later, they also helped calculate the orbit for putting the first American in orbit, which was John Glenn in 1962. Fun story about this is that this was the first mission that NASA actually used real computers, but the astronaut, John Glenn, didn't trust the computers. So he got the West Area computers to redo the calculations by hand to make sure that they were correct. And like, I would never trust myself to do a calculation over a computer these days. So that's impressive. That's obviously an amazing skill. And finally, of course, they were also there for putting the first people on the moon. specifically, Katherine Johnson not only calculated the trajectory of the flight to the moon, but she also worked on ensuring that this thing, the lunar module, would communicate and sync up with this thing, the command and service module, so that they could bring everyone home and safe. But of course, women have been involved exploring, charting the planets in the solar system, exploring them, but we're also looking for other planets. So this is Natalie Batalha. She is currently a professor of astronomy and astrophysics at UC Santa Cruz. And previously she was a research astronomer at NASA, who held the position of co-investigator and mission scientist for the Kepler spacecraft. And if you don't know about the Kepler spacecraft, come talk to me afterwards. I will be hanging out in the Meet an Astronomer section, because the Kepler spacecraft found a ton of exoplanets. And Natalie works on, characterizing the survey of Kepler, but also wants to understand what different populations of exoplanets can tell us about how planets form generally, which is something very near and dear to my heart and my research. And so finally, there's one last story I want to tell you today, and it's about this one. It's about this person, Malavia Maurice. She was a Serbian physicist who studied at the Swiss Federal Institute of Technology in Zurich, which is better known as ETH Zurich. It's a world-leading institute in Germany, and it was there that she met this guy. Now, for the uninitiated, this is Albert Einstein. They worked together while they were at ETH Zurich. They studied together. And eventually Einstein passes final evaluations, got his PhD, and left. He didn't get a job, so he went to go work at a patent office. Malavia struggled with her examinations and failed the first time. And then the next year she tried again, but she was 3 months pregnant with Einstein's child, and also didn't pass. They would go on to get married. And they were together when Einstein had his so-called miracle year of 1905, when he published four papers that made him a household name. These were on, of course, the photoelectric effect, Brownian motion, special relativity, and the E=mc² paper. Now, this is where the story gets a bit controversial, because from some accounts, Malavia and Einstein were close collaborators, and Malavia made significant contributions specifically to the paper on special relativity. For example, when Malavia was still studying, working to pass her qualifiers, and Einstein was working at the patent office, they would send letters back and forth to each other, and he commonly referred to his scientific ideas and processes as a collective thing. So he said in a paper in 1900, he said this: I'm also looking forward to working on our new papers. You must now continue with your investigations. How proud I will be to have a little PhD for a sweetheart when I remain a completely ordinary person. And of course, it's not the only time he did this. It's in a number of his letters, or this one from 1901. I'll be so happy and proud when we are together and can bring our work on relative motion to a successful conclusion. And, there are other accounts from Malavia's brother, for instance, of them working together furiously on this paper relating to relative motion at his estate. And they left, and she told him that, they made great big strides in their work. But, the reason it's controversial is that some historians of science disagree with this picture of them being close collaborators. Mainly because of the fact that she struggled passing her final exams, and that her grades weren't as good as other people's grades. There are also, in these letters that have been preserved, there aren't a lot of them from Malavia to Einstein, but of the ones that we know about, she doesn't usually talk about the work. She just talks about home life kind of things. But so even though there's not a totally clear answer to whether or not Malavia and Einstein were close collaborators, I still think it's an important story to tell, because there's so much in Malavia's story that just feels familiar and that resonates with people. She was a disabled woman who left her home and her family to pursue physics because she loved it. She got there, she was the only woman in her cohort, and she just was there during this time of intense inequality. It's not inconceivable to see how she would have been treated differently for being who she was. And from Einstein's own accounts, she was at least smart enough to edit his papers. He, in another letter, he said that after finishing a paper, he went to sleep for 5 weeks, and Malavia stayed up furiously for a week and edited everything and went over and pored over it again and again. So I think it's fair to say that she didn't have enough support to be successful. There were there's systemic barriers in her way. And when I think about Malavia, I wonder how many women have been pushed out of astronomy in the past, and how many women are being pushed out today because of similar or new barriers that exist. These things, they've existed for a long time, and they will continue to exist in the future. But I think it's our job to figure out how to address them, because we can certainly do way more cool astronomy if everyone has access. But of course, despite these barriers, there are way more women and gender minorities in astronomy than a person could ever fit into, a 35-minute talk. So here are a bunch of people that I looked into, but wasn't able to feature in the talk today. They all do amazing science. And, they all have these wonderful stories. So please look them up if you'd like. And if this kind of topic interests you, there are lots of things that go on. Here's some other resources. There's books like the one about hidden figures. Chanda Prescott-Weinstein also recently wrote a book called The Disordered Cosmos. The International Astronomical Union is hosting events for, the International Day for Women and Girls in Science, as well as International Women's Day that's happening throughout the period on the screen here. And you can look on their website for that. The Dunlap Institute is also going to be doing a Women in Astronomy themed trivia night coming up. So you'll have a head start on that. And if you're interested in STEM, there's various ways for you to get support at all levels. If you're a high school student in Toronto or Kingston, there's Girls to STEM. It's a mentorship program that pairs high school students with with women in STEM. There's the Ideas Initiative and the Supernova Foundation for if you're sort of a graduate student looking for support. And of course, there's the Canadian Conference for Undergraduate Women in Physics. So thanks for the opportunity to talk tonight. And I'm very happy to take questions.
Thank you, Taylor, for the great talk. That was really fun. And yeah, it's always great to learn, about like the history of science, and also, the history of people that, in our degrees, you don't actually ever really get to hear about. So it's really awesome to like be able to hear about all those things. I guess to start us off, the first question would be, is there any women astronomer that particularly inspires you?
Oh, so when I was there's a bunch of different women at different periods in my life. Currently, I'm very inspired by my supervisor, Yanchin Wu, because she's just like a powerhouse. Like, she just knows everything. She's one of these people that, can like see equations in the air. Like, she's a genius. When I was an undergrad, though, I was like looking for these people in the field who did like kind of these like niche things. And Sarah Seeger, who coincidentally did her undergraduate degree at University of Toronto and who I met during my first year of grad school. Mind-blowing. She was one of the big reasons. That she had a book that a textbook actually that she wrote, and I like pored over it during my undergrad. And she works on sort of like the astrobiological context. So she looks at what biosignatures are, how you can look at a planet and tell if there's life on it. And I thought it was just really cool that you could do stuff like that.
I guess a follow-up, especially because you also study planets. Is there like a short summary of kind of how you would, figure out like on an exoplanet, so planet not our solar system, like how can you try to figure out what it's made out of and things like that to be able to, make like figure those things out for if there are biosignatures or anything?
Yeah. So again, it's all spectra. So this story we told about, light from a star passing through a cloud, coming to our telescope, splitting it up. Instead of a cloud, you can just literally do that with an exoplanet atmosphere. So, let's say my light is the star. The planet passes in front of it, blocks light. My eye is a telescope. And some of that light, will go through the atmosphere of the exoplanet, and then you'll be able to see the imprint of the atoms in the atmosphere of the exoplanet, convoluted and all messed up with all of the elements that are in the star. But there are really smart people who can do things like figure out how to disentangle those. And it feels like magic. I don't understand it, but it's magical.
Yeah, great. Do you have any advice for any aspiring young girl or gender minority astronomers?
Yeah. Talk to people, find people who will support you and who can help you do the logistic things. I come from a family, my parents didn't go to university. I kind of had to figure out a lot of how to do astronomy and to do the university scene by myself. And finding these sort of like mentors was really crucial for my own development. So that's why things like Girls with STEM in Toronto is so crucial. And I think it's so important because just like figuring out how to do it is such a barrier sometimes. And then when you find someone who can really like lead you through those things, I think it's really important to like, see that and like seek it out. Yeah, I think that's probably the most useful thing to do.
Yeah, definitely. And I guess just like one thing to add on to that too for people is that, if you live near like a university or near like an observatory or planetarium, always reach out to like outreach events happening, or like if it's a planetarium, sometimes they'll get volunteers to help them do things. So always like email the people. Don't be afraid to do that. Because then you can get like really cool experience, like while you're still, young and in like grade school. Yeah. Okay, I guess a more sciencey question. On your periodic table of elements, you had a lot of them having different colors from different things that it could come from, but there was a couple elements that didn't have any of the colors in the legend. Where do we think those might have been formed from?
Plutonium. These two are only man-made. They only we can, these are the elements, we don't find them in the universe. I think they're like technetium. Do you know the name, Simran? I don't.
TC? No, I do not.
they're human made, so they don't exist in nature because they're so radioactive that if they were to exist, they would just decay right away. So we know about them, because we've made them. We've like been able to like decay things into other things and to like get them as a result, but they don't survive for very long. So that's why we don't really know. They probably are made, in these various like high energy things. But we just can't say if they're definitely made there because we haven't seen them made because they die so quickly.
Yeah, there's definitely some like elements that exist. Yeah, I guess another question on the periodic table since we're here. How do people, as you can see, like some of the colors, like there'll be smaller amounts of some colors and way more of others. Like how do scientists figure out, like this tiny amount of like, for example, from Big Bang fusion, whereas a lot of it's coming from dying stars. Like how do people figure that out?
Yeah, so I think you can from a given event, you can figure out, like what the relative amount that's produced during that event is. But of course, some events are more common than others. And so, you have one event that produces a lot of whatever this element is, Bi. Merging neutron stars produces a lot of it. And, it turns out they're like common enough, but dying low mass stars rarely die, they live forever. So dying low mass stars, it's probably less frequent than emerging neutron star. And so it might make also less of this. So that's why it's just a tiny little corner versus like a whole square.
Cool. I guess, yeah, you brought up neutron stars, and that reminds me of something else. You were talking about Dr. Maria Drout's, or I guess Professor Maria Drout's discovery of the colliding neutron stars, and you showed like the image where it was like this light and it was brighter and then it was less bright. How was she able to figure out that that is like merging neutron stars?
Yes. So the other part of this story that I didn't talk about, which is in the first sentence of the abstract, is that this event, they figured out that this event was happening because of gravitational waves. So gravitational waves are like a consequence of general relativity, where if you have two objects that are moving really quickly through space-time, they'll produce waves that you can detect with these like hugely complicated lasers that sit on the ground, and then a gravitational wave moves through it and the distance between them changes a little bit and they get misaligned, whatever. So this is actually an observational counterpart to a gravitational wave event. The gravitational waves were observed with LIGO on August 17th. And so this group was able to be like, we need eyes here because we think that there's a gravitational event coming from this place. And that's when they were able to turn the telescopes on. And that's when they saw this thing. That's why they didn't catch it any earlier too, because LIGO only sees the gravitational waves when they're at like sort of their brightest, their most intense. So yeah. That's also how they figure out the mass of the two things. That's another point. Yeah.
We can do multi-messenger astronomy. Like we can look at things like the light, but then we can also look at things like gravitational waves. So literally the space that we're existing in getting stretched and squeezed. It's really cool, at least in my opinion.
Yeah, it's wild because like most of astronomy is built on just seeing stuff with light. So like I don't think things can like things like it's like chemistry having a whole nother set of elements to work with. Like it's just mind-blowing what kind of like advancement that is. Yeah, field changing.
Yeah, it's definitely really cool. Yeah, well, I think that's all of our questions for tonight. Thank you again for the really amazing talk, and I encourage everyone to go and chat with Taylor some more. You can ask more about her research and stuff in the Ask an Astronomer room. And yeah, just quickly before we get there though. Oh, okay, great. So I'd like to say thank you to our volunteers. They all are helping with the demonstrations that we have after this, and also for organizing and running this event. And also, I would like to say thank you to our sponsors, because without them, we could not have these events. So please go visit our activities and demonstrations. The Zoom link should be being put in. And also, please fill out our feedback form at bit.ly/AstroTours. And see you next month on March 26th for our special Earth Hour AstroTour.